So this is the presentation, the implementation and evaluation of a secure keyless ignition and integrated control system for Arduino-based instrumented cars. Overview, we'll look at the aim of the project, the main features, the system architecture, that is the secure keyless ignition, the integrated mobile app, the GPS navigation feature, real-time passenger detection, the Bluetooth controlled window operation, and then we'll see the testing and conclusion and further works. Now, the aim of the project. The aim is to develop a secure keyless ignition and integrated control system for instrumented cars. Today, we live in an age of smart cars. Everywhere we hear self-driven cars, electric cars, hybrid cars, integrated with digital services. And these cars are also quite expensive, right, compared to traditional cars. However, it's also, we can note that traditional cars that make up maybe more than 99% of our roads are filled with traditional cars. These also could be retrofitted with IoT with a view to making them smarter, more secure, and more user-friendly. So here, we will consider Arduino-based instrumented cars. Right? So the aim of this project is to be able to retrofit these traditional cars to make them smarter. Right? So the main features of this project are keyless ignition system, RFID. Here we are using RFID because it's wireless, it's robust, and it's difficult to duplicate, thereby enhancing vehicle security. And also, the integrated control system can be accessible from a mobile app with a dashboard. And the dashboard will have access to all this ignition system, GPS, Bluetooth control windows, as well as real-time passenger detection. So this is the system architecture. You have the user interface from the mobile app that can access all these four features: secure keyless car ignition system, the GPS module, the passenger detection system, as well as the Bluetooth window operation system. And all of this will be controlled with the Arduino microcontroller, which will be interfaced with the car systems through electronics devices. And we'll have a look at all these electronic devices as well. Now, let's take one by one. So, secure keyless ignition. The primary elements are RFID reader and RFID tags. So, RFID is radio frequency identification, right? It works like this. So, the reader is connected to the Arduino microcontroller, and this is based inside the car. And this serves as a point of contact between the vehicle and the user. The user will carry the RFID tags. So, in this case, he will not carry the keys of the car, but then the tag. And this tag is used for authentication. The principle is simple. So the reader scans the tag when it is in proximity. It decrypts the embedded information using a secure decryption algorithm, and then verifies its authenticity. If the tag is authenticated, the reader signals the Arduino microcontroller to start the ignition process. Now, how secure it is, we have already embedded inside the RFID tags cryptographic techniques, and these are used to protect the data. And each tag is uniquely paired with the car's RFID reader. So it becomes very difficult for someone else, for a third party, to sort of steal the car without the tag. So essentially, the secure keyless car ignition system enhances the traditional ignition process by incorporating secure contactless technology. This is wireless technologies. And second big thing in this project is the integrated mobile app. So the mobile app controls. This is the unified control interface for the user. We have developed it for both for iOS and Android platforms, incorporating multiple functionalities, like the integrated dashboard, the keyless ignition, the navigation, the GPS navigation. This is quite common in cars today. Real-time passenger detection, as well as Bluetooth controlled window operation. Now the dashboard, it displays real-time data on vehicle parameters, such as speed, fuel level, engine temperature, amongst others. So this is normally connected to the OBD2 interface, that is onboard diagnostic. So this data is gathered from the vehicle's onboard diagnostic system, processed by the Arduino microcontroller and relayed to the mobile via a Bluetooth connection. The GPS navigation feature, now this is quite common in cars you have everywhere. So this is something that we have also implemented. The GPS navigation feature, it provides both navigation support and tracking functionality. So the vehicle's real-time position is plotted on a map using an integrated mapping service. Here we have used Google Maps, but other mapping systems also can be used. And GPS integration also provides a security feature in the form of tracking. So tracking a vehicle's position, the GPS can be used to locate the car if it's stolen or misplaced. And also you can get a history of vehicle's location. This can be recorded and accessed later if needed, further enhancing the safety and security aspect of the vehicle. So this also was implemented. Third, we have also implemented the real-time passenger detection. Now this feature, right, is not really necessary for a car, because in a car you can have 4 to 5 passengers, right? But it becomes interesting for buses, for vans, minivans, and also for trams, metros. And the system is the same, right? We have used pressure-sensitive seat sensors that were installed in the vehicle seats. And as soon as a passenger sits on the seat, the sensors detect the presence of the passenger based on the weight applied. So the pressure data is read by the Arduino microcontroller and interprets the pressure readings and determines if the seat is occupied or not. Now, this can also be interesting if it's a leasing company, you're leasing cars. And normally when you lease cars, you can put 4 to 6 passengers, but if the weight is much more than this, then you know that the leaser, right, the person who has leased the car is putting more passengers, right? So we have a proof of concept. So this also we can know at each and every point in time how many passengers are seated in the car. Another feature, Bluetooth controlled window operation. So here we have used servo motors installed within the window mechanisms of the car or the vehicle, right? So motors are controlled by Arduino microcontrollers, which interpret commands sent from mobile app and translate them into physical movement of the windows. So the user can select individual windows or all the windows simultaneously and command them to open or close to a desired level. So this control is represented in a simple intuitive layout within the app, using sliders to represent each window and its current state. So this also, it could be regarded as a fancy feature, but we have been able to do it. So we are making a proof of concept of how much, to what extent we can instruct cars, so that we can see whenever there's a need to do it, if the client is asking for it, be it for cars, buses, vans, minivans, even metros, we can use this similar technology to do it. Testing. So component level testing was done. So all the components were tested under multitude of conditions, reflecting realistic user environments. And also we have varied the factors such as vehicle speed, passenger count, GPS, signal strength, window operation. All these were controlled and varied to validate performance across diverse scenarios. So mobile app was subjected to a suite of usability tests, focusing on responsiveness, intuitiveness, and reliability. So we also ran tests simulating various operating conditions, such as low signal strength, high data traffic, to assess the application's robustness. So in fact, all the components were tested individually, and then overall, they were also tested in an integrated fashion. So the entire system was evaluated as a cohesive unit. This involved scenarios simulating real-world usage, including starting a vehicle, using the mobile app to monitor and control various parameters, navigating GPS, and also operating the windows. We did a lot of stress tests, like rapid consecutive stop sequence, simultaneous usage of various features, and also operation under varying conditions. So the objective was to ensure the system could handle high demand and adverse conditions without failure or performance degradation. In fact, all the tests worked well. Post some of the tests, we had to sort of tweak our system slightly, but at the end, everything worked fine. So we successfully developed and implemented an RFID-based secure keyless car ignition system and a comprehensive user-friendly mobile app interfaced for an Arduino-based car. So the overarching aim that is to enhance the security landscape of vehicular controls while simultaneously enriching the user interface, the user experience. Our security strength for integrative approach, it worked well. RFID performance worked well, and the entire system worked, but some weaknesses were there. So network coverage, when the network coverage is poor, right, the data couldn't be relayed, right? And also, whenever you have a lot of IoT devices, you have a lot of data, there is always a risk of security threats. So whatever data we are sending, we are encrypting them at the same time. Conclusion, we successfully implemented this RFID-based ignition system and also the control system. So enhancement of user security and user experience, achieving research goals, these are achieved. Now, some areas of improvement were identified, but potential for more advanced features, voice recognition, AI biometrics, power management improvements, integration with smart city infrastructure. So this will be future works. Some of the picks that we took during the work. So this is the ignition switch mechanism. Here we see the ignition startup wires, testing for 12 volts, the relays for the windows, FSR, this force sensitive resistor, this for the weight. So no load, it is the resistance is very low. When there's weight, the resistance becomes very high. So we have a lot of other pictures as well, but this was presented. Okay, thank you for attention. If you have any questions, we'll be happy to answer.